Hi everyone, today I'm going to talk about how the RANS turbulence models predict near-wall turbulence. The prediction of near-wall turbulence has been a big challenge for turbulence models since the wall in fact has several important effects on turbulent flows. For instance, the wall induces strong damping on velocity fluctuations and Reynolds stress terms, and also the turbulence is highly anisotropic near the wall. In this presentation, first I'm going to briefly present the RANS equations and turbulence closure problem. After that, the importance of accurate prediction of near-wall turbulence is discussed, and finally different methods that are used by RANS turbulence models to predict near-wall turbulence are presented. RANS equations are obtained by decomposing the instantaneous velocity and pressure values in the Navier-Stokes equations into ensemble mean and fluctuating components using the Reynolds decomposition technique as shown here. Here U prime and P prime are fluctuating components while U and P are ensemble mean components. Substitution of the decomposed values of the variables into the Navier-Stokes equations and performing the ensemble averaging of the resultant equations gives the RANS equations as shown here. The ensemble averaging of the Navier-Stokes equations has introduced new unknown correlation terms in the momentum equations, which are called the turbulent or Reynolds stress tensor, as we can see here inside the red square, and are written like this. Okay, we can see here. This term represents the transport of momentum due to the turbulent motion of the fluid flow and needs to be modeled. A large variety of turbulence models has been developed with an attempt to close the RANS equations by describing the Reynolds stress tensor. The reason why there is a large variety of turbulence models is that there is no single turbulence model that works for any general turbulent flow. This, in fact, makes the choice of a suitable turbulence model for a specific simulation a bit of a challenge. However, the key is that a turbulence model should provide a good trade-off between computational cost and accuracy. All of the RANS-based turbulence models face a big challenge which is in common between them, and that is the accurate prediction of near-wall turbulence, which we are going to discuss in this video. The importance of accurate prediction of near-wall turbulence is twofold. First, several quantities of interest are evaluated at this region, such as skin friction coefficient, heat transfer coefficient, and also in most cases wall is in fact the primary source of turbulence. Okay, wall in fact has several important effects on turbulent flows, which can be summarized as follows. First, no slip condition results in strong gradients on mean velocity components since it imposes zero velocity value at the surface. Additionally, imposition of damping on velocity fluctuations and Reynolds stress terms, as can be seen in this figure, which shows the results of a DNS simulation of turbulent flow inside a channel at a Reynolds number equal to 13,750. As we get closer to the wall, the velocity fluctuations go to zero. Impermeability of wall induces stronger damping on wall normal velocity fluctuations. We can again observe in this figure that the normal velocity fluctuations experience a strong damping effect due to the presence of the wall. And finally, turbulence is highly anisotropic near the wall. Once again, as can be observed in this figure, the velocity fluctuations are different, which highlights the turbulence anisotropy close to the wall. To highlight the importance of turbulence anisotropy close to the wall, it is worthy to mention that the most popular turbulence models in use calculate the Reynolds stress terms using the isotropic Boussinesq hypothesis as presented here. We can see the isotropic Boussinesq hypothesis here. In this equation, rho is the fluid density, K is the turbulent kinetic energy, and delta Ij is the Kronecker delta function. Sij is the mean strain rate tensor, which is expressed in terms of the gradients of the mean velocity components as shown here, okay? And also nu T is the turbulent eddy viscosity, okay? As can be seen in this equation, the Reynolds stress terms are defined as linear functions of gradients of the mean velocity components. In other words, it is assumed that there is an alignment between the Reynolds stress terms and the mean deformation rate of the flow. More precisely, it is assumed that the difference between the turbulent shear stress angle gamma tau as defined here and the flow and the turbulent flow gradient angle gamma g as defined here is equal to 0, okay? This is exactly what the isotropic assumption is all about. However, as we can see in this figure again, turbulence is highly anisotropic near the wall. It is worthy to mention that the zero equation turbulence models, such as the mixing length model, one equation models, such as the Spallard-Almaras model, two equation turbulence models such as the K epsilon and K omega, and all of their variants calculate the Reynolds stress terms using the isotropic Boussinesq hypothesis. Therefore, by default, all these turbulence models, as we mentioned here, are unable to capture the near wall turbulence anisotropy. Capturing these wall effects on turbulence is still challenging for turbulence models, and usually highly refined grid is necessary. So the question that arises here is that how the turbulence models capture these wall effects that we just mentioned. Before answering this question, it is worthy to mention that experiments and mathematical analysis have shown that the inner region of the boundary layer next to a wall can be split up into three sublayers: viscous sublayer, buffer sublayer, and logarithmic sublayer or log-law sublayer as shown in this figure, okay? To define the extent of these sublayers, the non-dimensional wall distance y plus, which is defined here, and the non-dimensional velocity u plus, which is defined here, can be used, okay? Here y indicates the distance from the wall, vp is the component of the velocity parallel to wall, and u asterisk is the reference velocity. In the innermost layer, the so-called viscous sublayer, which as shown in this figure is associated with y plus values less than 5, the flow is almost laminar-like, only the viscosity plays a dominant role in the fluid flow. In this sublayer, the relationship between the y plus and u plus is as shown here. Further away from the wall, in the log-law region, as we can see here, in which the y plus values are larger than 30, the turbulence dominates the mixing process. In this sublayer, the relationship between the y plus and u plus is as shown here. In this equation, the coefficient k is the von Karman constant, and E is an empirical constant. Finally, in the region between the viscous sublayer and logarithmic sublayer, there is a buffer layer where the effects of molecular viscosity and turbulence are of equal importance. How the turbulence models deal with the near wall region determines that these models are whether high Reynolds number turbulence models in which a high Y plus wall treatment is used, or low Reynolds number turbulence models in which a low Y plus wall treatment is used. And finally, there are some models, especially the two-layer turbulence models in which an all Y plus wall treatment is used. So what comes next is a brief explanation about how each of these turbulence models capture the wall effects. Okay, first let's talk about the high Reynolds number turbulence models. In these models, the velocity is obtained using the wall function as shown here. Therefore, the center of the first cell immediately next to the wall should lay within the logarithmic region of the boundary layer, which is equivalent to Y plus values between 30 to 500. The turbulence boundary condition consists of zero normal gradient for the turbulence kinetic energy, and the turbulence dissipation rate is calculated by assuming an equilibrium condition, which means that the turbulent production, as we can see here, is assumed to be equal to dissipation rate. Note that K here is the von Karman constant. As an example of these models, we can mention the standard K epsilon turbulence model, which is the most popular turbulence model in CFD community. This model solves two separate transport equations, one for the turbulence kinetic energy K and one for the turbulence dissipation rate epsilon, as shown here. Here is the transport equation for K and here is the transport equation for epsilon. In these transport equations, we can see the transient term or the rate of increase as shown here, the convective term, diffusive term, production term, and finally the destruction term. From these transport equations, K and epsilon are calculated, which are used to estimate the eddy viscosity as shown in this equation. Okay, C mu is the model coefficient. As mentioned earlier, this eddy viscosity that is calculated from this equation is used later to calculate the Reynolds stress terms using the isotropic Boussinesq hypothesis, as we can see here. The main advantage of using the high Reynolds number turbulence models is the elimination of both iterative convergence problems and the excessive calculation time. However, there are some shortcomings associated with the high Reynolds number turbulence models, which are as follows. First, the log law assumption is valid for a very special flow condition, such as attached boundary layer and zero pressure gradient. Hence, it is not applicable to non-equilibrium flows such as stagnation and separation. And also, the Y plus is a flow-dependent quality, so it is difficult to ensure a fixed Y plus value larger than 30 for all of the near wall cells. We might also have Y plus values in the buffer region where the profile is not known very well. For instance, this figure here represents the distribution of Y plus values over the surface of an underwater vehicle where an attempt has been made to use a high Reynolds number turbulence model. As can be seen, although the Y plus value is mostly larger than 30 over the body surface, there are some regions where the Y plus is significantly smaller than 30. Now let's talk about the low Reynolds number turbulence models. In these models, the velocity is obtained using this relation, and therefore the center of the first cell immediately next to the wall should have a Y plus value of around 1. These models use three different approaches to model the wall damping effect on turbulence, which are presented here. The first approach is the low Reynolds number approach. This is the most common approach in which a damping function is applied to some or all the coefficients in the equations constituting the turbulence model. As an example, in the Spalot-Almaraz turbulence model, a damping function f nu1 is used to relate the modified diffusivity to eddy viscosity as shown in this equation. The Spalot-Almaraz turbulence model, which is a one-equation turbulence model based primarily on empiricism and dimensional analysis, solves this transport equation here to determine the modified diffusivity, which is related to the turbulent eddy viscosity using this equation. Okay, here P is the production term and S is a user specified source term. F nu1 is defined here. Okay, we can see f nu1 here, and here we can see the behavior of this damping function with respect to chi. Another example is the low Reynolds number K epsilon turbulence model, in which the coefficients are defined as functions of a turbulent Reynolds number, often also incorporating the wall distance. Okay, here we can see the definition of these coefficients highlighted in red for both the standard K epsilon low Reynolds number model, which is shown by SK, and Abe-Kondo-Nagano K epsilon low Reynolds number model, which is represented by AKN. The definition of the Reynolds numbers used in these coefficients, as we can see, are given here. Okay, the first Reynolds number is based on the wall distance and the root square of the turbulence kinetic energy. Okay, here also we can see the turbulent Reynolds number, and finally the Reynolds number based on dissipation rate. The second approach, which is called the two-layer approach, is solving different equations near wall for one or more turbulence variables. As an example, we can mention the two-layer K epsilon turbulence model. The computation is divided into two layers. In the layer close to the wall, both the dissipation rate and eddy viscosity are specified as a function of wall distance. However, the equation for the turbulence kinetic energy is solved across the entire flow domain. Okay, several types of two-layer formulations have been proposed, but here two of them are presented. One for shear-driven flows, as we can see here, and one for buoyancy driven flows. D indicates the distance to the wall. RED is in fact the wall distance Reynolds number. L epsilon is the turbulence length scale, and the dissipation rate is defined using this equation based on turbulence kinetic energy and length scale. Then the eddy viscosity values are blended smoothly with the values computed from the transport equations used for the layer far from the wall, as shown here. Okay, so here we are blending smoothly the values of eddy viscosity for the layer far from the wall with the layer close to the wall. Lambda here is the blending parameter, which is defined in this equation. Re asterisk y is the model coefficient. The third and last approach, which is called the elliptic blending approach, is solving additional equations to consider the wall effect without using damping. This approach provides a more physical model for wall damping effects. Turbulence 1993 proposes elliptic relaxation of the pressure strain term for the Reynolds stress turbulence models to capture the non-local influence of wall on pressure fluctuations. In this approach, damping is enforced through elliptic equations to reflect the elliptic nature of pressure rather than algebraic expressions in terms of wall distance. So the model doesn't require the computation of the wall distance, and it is more suitable for complex geometries. The asymptotic behavior for each Reynolds stress term is correctly reproduced. However, it increases the computational cost since we need to solve 6 additional transport equations for each Reynolds stress term. Thus, in 1995, Turbulence proposes an elliptic relaxation formulation for the eddy viscosity models, which is commonly referred to as V2F K epsilon turbulence model. To determine the eddy viscosity, this model, in addition to turbulence kinetic energy and turbulence dissipation rate, solves 2 additional transport equations for 2 more turbulence quantities. First is the wall normal stress component V2, and also the elliptic relaxation parameter F, as we can see here, right? Here we can see the transport equation, which is solved to obtain the wall normal stress component, and also here we can see the F equation. Okay, the P terms here are the production terms. Okay, and L here is the turbulent length scale. The V2 here, wall normal stress component, is responsible for modeling the velocity fluctuation normal to the streamlines and gives the correct representation of the wall damping effect on turbulence. Additionally, the elliptic relaxation function F, we can see here, is responsible for modeling the anisotropic wall effects. In this model, the eddy viscosity is modeled using this equation. Here, C mu is the model coefficient and T indicates the turbulent time scale. The V2F model is designed to capture near wall effects. It is known to capture the near wall turbulence effects more accurately, which is crucial for the accurate prediction of heat transfer, skin friction, and flow separation. But it is still an eddy viscosity model far from the wall. Further, it is computationally expensive since it solves 2 additional transport equations. Okay, Manso and Hangelich in 2002 proposed a new formulation for Reynolds stress turbulence models to make the model proposed by Durbin in 1993 more industry friendly and to get rid of the F equation, which in fact was causing a lot of problems. They replaced the F with a scalar function alpha, which reflects the elliptic relaxation. So this elliptic equation is solved for alpha, which is 0 at the wall and 1 for the region far from the wall. This in fact has led to the development of the elliptic blending Reynolds stress turbulence model of Lardo-Manso, which I will present later in another video. Likewise, in 2012, Billard and Lawrence extended the V2F model by replacing the F with the scalar function alpha, which reflects the elliptic relaxation. So this elliptic equation is solved for alpha. The model developed by Billard and Lawrence 2012 is called BL-V2 divided by K. This model is known to be robust for complex flow geometries. Note that the elliptic blending models generally show an improved universal near wall behavior. The all y plus wall treatment uses a wall function for coarse grids. We can see here where the y plus values are larger than 30 and also resolves the viscous sublayer for fine grits. We can see here where the y plus values are smaller than 1. Okay, and also by appropriately blending the viscous sublayer and logarithmic sublayer, this approach produces consistent results for cases where the cells immediately next to the wall fall within the boundary layer's buffer region. So the summary of what I talked about in this video, we learned that what the turbulence closure problem is. We also learned about the importance of accurate prediction of near wall turbulence, as it is related to several quantities of interest at this region, such as the skin friction coefficient, heat transfer coefficient, and also in most cases wall is in fact the primary source of turbulence. And finally, we learned in a rather comprehensive manner that how the high Reynolds number turbulence models, low Reynolds number turbulence models, and two-layer turbulence models predict the near wall turbulence. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.